Okay, so hi everybody. So today we're going to go ahead and start episode 2 of 5-Minute Math. And today we're going to be working on Vieta's formulas. Okay, so Vieta's formulas. Uh, so I'm not going to go over the derivation of the formulas right now. I'm just going to jump in and use those. You can go ahead and take a look at the supplemental video that I'm going to upload to YouTube as well to go ahead and explain where those are and what you need to do to memorize those or to work them out every single time. Okay, so the first question we're going to get to is what is the product of the roots of the quadratic equation? Okay, so what we know is by Vieta's formula, we know two things. We know that the sum of the roots, and here you should know that there are two different roots, right? Two different roots because the fundamental theorem of algebra. So the sum of the roots is going to be equal to negative a of n minus 1 all over a of n. And I know the product of the roots is going to be equal to negative 1 to the power of n, a naught all over a n. And you simply have to have those formulas memorized. So here we're doing the product of the roots. Now this one wouldn't be too bad. We could actually just solve this and go ahead and multiply them out. But we're going to go ahead and do it using Vieta's formulas because, well, that's what we're practicing. Okay, that's what we're doing. Okay, so product of the roots. So I'm going to use this. So the product of the roots here is going to be negative 1 to the nth power. This is a second degree polynomial. So this is raised to the second power, a naught. So in this form, what I have is I have a2x squared plus a1x plus a naught is equal to 0. So that's what we have. Okay, so here a naught is going to be the constant term. So that's 36. And then divided by an. An is representative of the leading coefficient. So in this particular case, it's going to be a2. So we have over 2. So this is 36 divided by 2 gives me 18. Okay, and you would get the same answer had you actually just solved that and then multiplied them together. Okay, number 2. If the two roots of the quadratic equation x squared minus 12x minus 2 are equal to 0, and alpha and beta the roots are alpha and beta, what is alpha squared plus beta squared? Okay, this is a pretty tricky one, and it's pretty clever how this actually works out. And like I said, very classic type of a problem here. Okay, so we have two different things here. We have the product of the roots. So the product of the roots is going to be alpha times beta. But in this instance, going back up here and using this formula, I'm going to have negative 1 to the power of 2 because this is a second order polynomial. A naught, right, because that was the formula. So A naught in this case is negative 2 all over an, and an is 1. So all over 1. So this is just simply going to be equal to negative 2. Now the sum of the roots, which is going to be alpha plus beta, is going to be equal to, by this formula up here, negative a of n minus 1 all over a of n. So this is negative a of n minus 1. So this is a2, a1. So this is going to be negative 12. And then all over a of n, which is 1. So you just get that. So you end up with just positive 12. Now this is great, but this doesn't help me get what I need. I want alpha squared plus beta squared. So what I do here is I take this and I square it. So I'm going to take alpha plus beta. I'm going to square it. And by doing this, I end up with alpha squared plus 2 alpha beta plus beta squared. Now look, alpha squared plus beta squared. Well, that's what I want. So I'm going to go ahead and subtract that to the other side. So I have alpha plus beta squared minus 2 alpha beta is equal to alpha squared plus beta squared. Well, that's what I want. So now I just need to know, well, what is alpha plus beta? I know what alpha plus beta is. It's 12. So this is going to be 12 squared minus 2 times alpha times beta. What is alpha times beta? But it's negative 2. So this is times negative 2. So this is equal to 144 plus 4, which gives you 148. Okay, it's pretty classic trickery there. Some good questions. Okay, so 3. Let A, B, C, and D be the roots of this. Find the value of all of this. Okay, so this is a little bit trickier. But before I get going with this, I'm going to go ahead and I'm going to find a common denominator here. So the common denominator between AB, AC, AD, BC, BD, and CD is ABCD. Oh, and that's the product of all the roots, right? So rewriting this, this is going to be, so this is missing a C and a D. So this is going to be C, D plus, this is missing a B and a D. This is missing a B and a C. That's missing an A and a D. That's missing an A and a C. And this is missing a and a B. And this is going to be all over A, B, C, D. Well, sweet. Look, this product of the roots. Super easy. So the product of the roots here is going to be equal to A times B times C times D. And by that formula that we had up here, this is going to be -1 to the 4th power times A naught. Well, A naught is the constant, so that's just 4 all over the leading coefficient, which is 1. So that is simply just going to be 4. Okay, so the bottom number there is just going to be 4. Okay, now what about all of this? Now I'm going to rewrite this. And once again, I suggest that you go back and rewatch the video explaining what Vieta's formulas are. There's actually n formulas. N formulas? It should be n formulas based off of what the degree of the polynomial is going to be. Okay, so here's what we're going to do. I'm going to rewrite this as, I'm going to rewrite it as A, B plus A, C plus A, D. What I've done is I've exhausted all the ones with A's in them. Okay, there's an AB, AC, and then AD. Now, in addition to that, I'm just going to put these in parentheses here. Now I'm going to start off with B, and I'm going to match B's up. I'm going to put all the ones that have B's in them. So I have BC plus BD, right? BC and BD. And the last one I have is CD. Okay, and this is all over what we said before, which was 4. Now, this is not one of the formulas that I gave you earlier. Okay, this is not one of them. But one of the other formulas, and like I said, there's a whole bunch of different formulas here, and you need to go back and watch the video to explain the Vieta's formulas, is one of the other formulas is you'd basically take, if you have all the roots, you have A1, so there are n roots, and the n roots are A1, A2, A3, and so on. So you have A1 times A2 plus A1 times A3 plus all the way up to A1AN. Okay? So in other words, I took all the A1s and I matched them with all the rest of the roots. Kind of like what I did here. Actually, exactly what I did there. Okay? Plus, so now we're going to do all the A2s. So you have A2 times A3 plus all the way up A2 times AN. Just like I did right here. I took all the A2s and I matched them up with everything else. Plus, and I basically continue this pattern, right? The next one would be A3 times A4 plus A3 times A5, and I would just continue out that pattern. I just do that all the way out until the very last one, as I have A of n minus 1 times A of n. So A of n minus 1 times A of n. And this is equal to A of n minus 2 all over A n. Okay, once again, you really need to go back and rewatch the videos here. Okay, so there it is. I just have to take the second one, actually A of n a of n minus 1, a of n minus 3. So the third one in. So the third one in here is going to be 9. So this is going to be 9 all over a of n, or the leading coefficient, which was 1. So it's just 1. So this just turns out to be equal to 9/4. Oops, sorry, I didn't put that last part in there. It's just equal to 9/4. This whole entire thing here was equal to 9. That's equal to 4. So we just end up with 9/4 as our answer. Okay. So there you are. In the Google Classroom, I have given you 3 new questions to work on. The first one, you don't really even need to use Vieta's formulas, but the next 2, you do need to use Vieta's formulas. Okay. All the best. And like I said, go ahead and watch the video explaining what Vieta's formulas are. Okay. So until the next episode, enjoy, and we'll see you soon.